In the previous case, we had seen how to use Gauss quadrature integral for one-dimensional problems. Now suppose say if we have a two-dimensional problems in which our domain is changing in both the directions, then in that case we'll see how to use this Gauss quadrature integral. So the formula which we had seen last time was for 1D. Now for 2D, what will happen is, for two-dimensional case, what will happen is our domain will change not only in one direction, that is xi direction, but it will also change in eta direction, and that is usually it is this kind of problems are seen in double integral or area problems, in area problems. So basically the methodology remains same. We need to evaluate first, we need to find first how many points, Gauss points, we will require to evaluate the given integral exactly. But in this case we'll have to check the exact Gauss points in both the direction, that is xi as well as eta. So therefore we have two Gauss points here, m and n. And then if I try to understand it, let us try to understand it in this figure. So let us say if it turns out that we require only one Gauss point in xi direction as well as in eta direction in order to evaluate the integral correctly. So then basically what we will do is we will evaluate this value, we will evaluate this value only at one point, wherein basically if say it is only at one point, that means we will evaluate this integral only at this point, at the origin of xi and eta. But let us say we by for a given problem we find out that n is 2 and also we get m as 2, then in that case we will have to integrate this, evaluate this integral in such a way that it is well balanced over both the coordinates, that is xi and eta. So what we'll have to do is, since in xi direction also we need to evaluate this integral at 2 points which should be balanced, so that means it should be somewhere here and somewhere here, and then in eta direction also we need to evaluate at 2 points somewhere here and here. Then therefore our total integral points, or the points where we will be evaluating the function, will be 4. One will be this, one will be this, one will be this, and one will be this. Basically why this is 4 is, it is nothing but n cross m. So if I get two Gauss points in say eta direction and two Gauss points in xi direction, that means we will have to evaluate this integral at n cross m points, that is 2 into 2, 4 points. So this and this will take care of the Gauss points in xi direction, whereas this and this will take care of the Gauss points in eta direction. Suppose say for a given problem it turns out that n is 3 and m is 3, then the three points, there should be 3 points in xi direction and 3 points in eta direction. Therefore the total points at which the integral will be evaluated will be 9, and that can be located in this fashion: 1, 2 and 3, and then the 3 this side and also 3 this side, so it will be 3 this side. So altogether we'll have to evaluate it at 1 2 3 4 5 6 7 8 9, 9 points. Let us try to understand this in detail by considering a problem. So we have this example here. It is already in terms of, it is already given in terms of the natural coordinates. So here we did not change we did not change the domain from given coordinate to the natural coordinate. But even if it was not given in terms of natural coordinate, we know very well how to change it. So only thing is, what we need to make sure is, now how many Gauss points we will consider in xi direction and how many Gauss points we will consider in eta direction. We had seen this table last time. So let us see how. So this basically m Gauss points now is in xi direction, but we also have here eta direction. So n Gauss points also will be considered in eta direction, and there will be corresponding weights for the Gauss points in eta direction. So what we will do here is, let us find first what is m and what is n. M is the number of Gauss points for in xi direction, and n is the number of Gauss points in eta direction. So let us first find the number of Gauss points in xi direction. If I look at the function here, the function here is a function of xi and eta. and xi and eta, and it is nothing but xi square plus xi times eta multiplied by eta to the power of 4. And then if I try to locate, or if I try to find how many Gauss points will require in xi direction, then we know the thumb rule: 2m minus 1. M is the number of Gauss points in xi direction, is equal to the highest degree here in this polynomial on xi is 2, right? So this is equal to 2. So from here I get this m as 3 by 2, which is nothing but 1.5. So number of Gauss points will be, it should be greater than the decimal value, so it will be 2. So the minimum number of Gauss points which I require in zeta direction, in xi direction, is 2. And then let us see how many number of Gauss points we require in eta direction. So number of Gauss points in eta direction is given by n, so 2n minus 1. And the highest degree of polynomial in eta direction, if I take this inside, it will be this eta and this eta raised to 4. So this will basically give me xi square eta raised to 4 plus xi eta raised to 5. So highest degree here in this polynomial on eta is 5. So this 2n minus 1 will be equal to 5. So this tells me that n is equal to 6. 2n is equal to 6, so n will be 3. So the number of Gauss points in eta direction is 3, whereas the number of Gauss points in xi direction is 2. So this tells me that I require only 2 Gauss points in xi direction, whereas I require 3 Gauss points in eta direction. So if I require 2 Gauss points, only 2 Gauss points in xi direction, it will be nothing but minus 0.57735 and plus 0.57735. By the way, if just to remind you all, here this coordinate varies from minus 1 to plus 1, and this coordinate varies from minus 1 to plus 1, right? And this is 0 comma 0. That is how the natural coordinate system works. So since I require 2 Gauss points in xi direction, they will be these 2 points. So one will be here and one will be here, but I require 3 Gauss points in eta direction. So 3 Gauss, since there are 3 Gauss points in eta direction, it will be this point. So one point will be at 0, which I have correctly taken. The second point will be at minus 0.77459, which will be somewhere here. So it will, second points will be here, and the third point will be at plus 0.77459. Sorry, this should have been plus, and the minus will be here, right? So basically I get here m cross n, that is 2 cross 3, that is 6 Gauss points. Altogether I will have to evaluate this integral at 6 points, since it is two-dimensional problem. So 1 2 3 4 5 and 6. So basically I need to evaluate this integral at 6 points in order to evaluate this integral properly. So, and this can be very easily done if I put everything in the tabular form, and it can be put in this fashion. So basically I have total of 6 points here, 2 cross 3, that is 1 2 3 4 5 6. So I'll have to write here the points as 1 2 3 4 5 and 6. The number of points in xi direction is only 2, that is minus 0.57735 and plus 0.57735. So if I look at this point, the coordinate of this in xi is minus 0.57735. The coordinate of this point in xi is also minus 0.57735. The coordinate of this point in xi direction is also minus 0.57735, whereas the coordinate of this point, and this point in xi direction is plus 0.57735, whereas the coordinate of this points in eta direction is 0.0.77459, whereas the coordinate of this point in eta direction will be 0, whereas the coordinates of this point in eta direction will be minus. So basically what I'm trying to say here is, this point, Gauss point of eta direction, will be there with eta direction in at 3 locations, here, here and here. right? Again I'll repeat, this point, this Gauss point of xi direction will be there with this points in eta direction at 3 points here, at this place, at this place, and this place, whereas this point of xi direction will be there with the points in eta direction at again 3 places, at this, and at this. So basically I need to repeat this point 3 times here and this point 3 times here. So that is what exactly I'll be doing here. I'll write this as minus 0.5 7735, and I will repeat it 3 times, minus 0.57735 minus 0.57735, and then I will write this 0 plus 0.57735, 0.57735, and 0.57735. And then now let us write this values, the values of eta. So since I already written the values of xi, now I will write the values of eta, because I require 3 points in eta direction. So those 3 points will be this. So this will be minus 0.77459, minus 0.77459, 0, and then plus 0.77459. And similarly here I will have to repeat that, minus 0.77459, 0, and then plus 0.77459. If I just compare this with this diagram, then this point minus 0.57735 and minus 0.77459 is nothing but this point. If I take this point minus 0.7735 and 0, it is nothing but this point. And if I consider this now, minus 7 minus 0.57735 and plus 0.77459, it is nothing but it is this point, right? Similarly, if I try to check this 0.57735 and minus 0.77459, it is nothing but eta is minus, xi is plus. That means it is this point, that is eta is plus, xi is minus. Similarly, if I look at this, then zeta, this xi is plus, whereas eta is 0. Xi is plus, eta is 0. That means it is this point. And then this, where both are plus, it is nothing but this point. So I have taken care of all these 6 points with these combinations. So this is how I'm supposed to write this. Now this is nothing but this table is nothing but I need to evaluate this given function. I need to evaluate this given function at this particular values, this particular combinations of xi I and eta j. So for example, f of xi I and eta j is nothing but this function, that is xi square eta raised to 4 plus xi eta raised to 5. So what I will have to do is, in order to fill this, I will have to use xi value as this and eta value as this. So it will be minus 0.57735 square times eta is minus 0.77459 times 4, then plus again I have xi, that is minus 0.57735 multiplied by eta raised to 5. So eta is nothing but minus 0.77459, and this value will be approximately equal to 0.281. So I can write this value as 0.281. Similarly, if I substitute these values here and then if I try to calculate what is the value of this function for this value of xi and eta, I will get this value as 0, because there is zeta here, there is zeta here, and irrespective of what is the value of xi, it will be 0. If I substitute this value, I'll get this as minus 0.041. And then similarly if I try to substitute all these values, I will get this as minus 0 point again 041. This value will be again 0, and then finally this value will be 0.218. And then if I look at the corresponding weight of xi I, the xi I weights were, for this minus value the weight was 1, and even for plus value the weight was 1. So if I just substitute the values of weight of xi I, for this all three the weights were 1, and for this all three the weights were 1, right, from here. And then similarly the weight for this weight and the weights for this eta points, that is minus 0.77459 plus 0.77459, here the weights are this. So this will be 0.55555, right? And then this will be for this second point, that is for 0, the weight is 0.088888. This will be again 0.55555, and then again this is 0.55555. This will be 0.88888, and this will be again 0.55555. And then finally here I want the multiplication of all these three quantities, this and this, and if I multiply them up, you can try it. This value will be 0.1561, this value will be 0 because this value is 0, then this value will be minus 0.02278, then this value, if I multiply all these three, this value will be minus again 0.02278, this value will be 0, and then finally this value I'll get it as 0.15611. Now finally what I want is, after getting all this, I just need to sum them up. I have got now this values, all the six values I have got here, right? 1 2 3 4 5 6, and then finally what we need to do is we need to just sum them up. We need to sum them up, and if I just sum them up, I'll get this as 0.26666, and this is the value of the integral of this integral I have evaluated just by using the Gauss Quadrature Integral. And then if I just compare it with the exact solution, if I had evaluated it with exact solution, if I had evaluated this exactly, then I would have got the value of this as 0.26667, and here with the numerical method I have got this as 0.26666. So it is a very close value. It is a very good value. So this is how we can use the Gauss Quadrature Integral to evaluate any integrands which varies from -1 to +1, that is they should be in terms of natural coordinate. But if they are in other coordinate, the way we had seen last time, if they are in other coordinate, then we have to use something called as mapping function. For example, let us just for the sake of example, let us consider here one more example. That is, suppose say if I have r is equal to integral -4 to 4, then integral 2 to 3, and then this is 1 minus x whole square 2 minus y square dx dy. If I have this integral, I know that I cannot directly use the Gauss quadrature formula here in this case, because they are not in terms of natural coordinates. The domain is not varying from -1 to +1. So what I can do is I can straight away use the mapping function, which will relate this coordinate system with natural coordinate system. That is, x is equal to xj minus xi by 2 times xi plus xj plus xi by 2. And then if I use this for x, if I use this, my x is varying from 2 to 3. X is varying from 2 to 3. So if I just substitute this, xj is 3 minus 2 by 2 times xi plus 3 plus 2 by 2, which will give me xi by 2 plus 5 by 2, and then therefore this will give me dx as 1 by 2 d xi. So what I basically need to do is, I need to, wherever there is x term, I need to substitute x as xi by 2 plus 5 by 2, and then this has taken care of x coordinate. But there is one more coordinate here, y coordinate, and I need to do the same thing here. Y will be yj minus yi by 2. Then here I'll call this natural coordinate as eta plus yj plus yi by 2. Here now yj is nothing but 4 and yi is nothing but minus 4. So this will be 4, then minus of minus will be plus 4 by 2 times eta, plus this will be 4 minus 4 by 2. So this y will be 4 times eta. Therefore dy will be 4 times d eta. This dy will be 4 times d eta. So how I can now replace this given integral in terms of natural coordinate is that, now since we will be substituting in place of x as this and dx as this and then y as this and dy as this, I can straight away switch the coordinate system from minus 1 to plus 1, and this will become 1 1 minus, in place of x I will substitute this as zeta by 2 plus 5 by 2 whole square into, multiplied by 2 minus, in place of y I will have to substitute it as 4 eta, and this will become whole square. This will be, in place of dx I will have to substitute 1 by 2 d zeta, and in place of dy I will have to substitute 4 times d eta. So finally I can write this as minus 1 to 1 and minus 1 to 1. This will become 2 and 2 4, this will become 2 times, and this will become 3 plus 3 plus zeta by 2 the whole square, multiplied by 2 minus 4 eta the whole square d zeta d eta. And once I get this given integral in this form, I can straight away then start finding what is m and what is n, then again the procedure will be same. Once I find what is m and what is n, then again we'll have to locate for particular m and n what will be our Gauss points and weight, make this table, substitute it, and then finally find the value of the given integral.